Okay, now let's take a look at the variance. Remember again that our random variable for this example was the number of cars at the intersection between 7 o'clock and 7:05 p.m., okay? And now, let's say we want the variance of y, okay? Sigma squared. What is the variance of this random variable y? Well, in general, we said that that was the difference between random variable y and its mean squared, and we want to take the expected value of that. Okay, what's the expected value of this difference squared? How different is this random variable from its mean? This random variable has uncertainty associated with it. It has several different realizations, each with a probability, and this mean stays constant. So how disperse are these data? How different is each one of those realizations from the mean of the distribution? Okay? So to find this, we need to use algebra. We need to use the FOIL method on this thing inside. Okay, so if we use the FOIL method, first, outer, inner, last, we should get y squared minus 2 mu y plus mu squared. Okay, and we're going to take the expected value of that. Okay, to go next, we just take the expected value of each one of those terms. So this is the expected value of y squared minus the expected value of 2 mu y plus the expected value of mu squared. Okay? Expected value of y squared, that just stays the way it is, right? This is a random variable, and we can't do anything more with this. But this is a little bit different, right? We have a 2 out here, we have a mu, and we have a y. The 2 is a constant, doesn't change. The expected value of 2 is always 2. Okay? So we could bring that out front. The mean, mu, the expected value of the mean doesn't change, or pardon me, the mean doesn't change. So its expected value is always just mu. We can bring that out front. It's not a random variable. This is not random, this is not random. So their expectation is just constant. They can come outside the expectation. Then we're left with the expected value of y. Okay, this is the random variable, and the expectation does mean something here. Then finally over here, we've got the expected value of mu squared. Mu squared is just a constant here. So the expected value of mu squared is just mu squared. Okay? So now what do we have? We have the expected value of y squared. We have 2 mu times the expected value of y. What's the expected value of y? Mu. So we've got 2 mu times mu, or 2 mu squared, plus mu squared. Okay? So what do we get here? Negative 2 mu squared plus mu squared. That leaves us with negative mu squared. So the variance here is the expected value of y squared minus mu squared. Another way to say that is the expected value of y squared minus the expected value of y quantity squared, because mu is the expected value of y. So this is the general formulation for the variance of a random variable. So now what are the implications for us? We have that particular traffic example, number of cars at the intersection of 9th Street and Kahika in Pawhuska, Oklahoma at 7 p.m. And we want to find what's this variance value there, okay? So we go over here, and that's the expected value of y squared minus the expected value of y quantity squared. Well, here we've got just y squared, okay? Each realization, squared times the probability that that realization occurs, summed across all realizations, minus mu squared, okay? And what did we say mu squared was last time? We said mu was 1.36, okay? So now we just have to implement this calculation, okay? There was a range of realizations of the number of cars at the intersection, and it ranged from 0 to 5. Okay, so we're going to say 0 squared times the probability that 0 occurred, that was 0.36, plus 1 squared times the probability that 1 occurred, that was 0.28, plus 2 squared times 0.15, plus 3 squared times 0.1, plus 4 squared times 0.07, plus 5 squared times 0.04. And from that, we're going to subtract off 1.36 squared. So for these cars that are at the intersection of Kahika and 9th Street, between 7 o'clock and 7:05 p.m., we've got a variance that would be the difference between these two numbers, which is 2.05, and that's in cars squared, okay? That's the number of units of our random variable squared, because we're in squared units here with a variance, okay? If we wanted to know the dispersion, this variability in the units of cars, we could take the square root of variance, okay? That would be the square root of 2.05, which is 1.43, and that's in cars, okay? So what's the standard deviation of this random variable y? 1.43 cars.